Here are some select Moodle Quiz 4 sample problems. Number 1. The rate constant of a certain first-order reaction is 45.9 seconds to the negative 1 at a temperature of 300 Kelvin. What is the value of the rate constant at 310 degrees Kelvin if the activation energy is 81.0 kilojoules? So first we want to look at our note card of equations that involves activation energy, which would be this one. And we're dealing with two different temperatures, so you want to use either equation 3, 4, or 5. We're asked to determine one of the two rate constants, so I'm going to use equation number 3 for this problem. Now I'm going to take this and I'm going to separate them. The natural log of the numerator, which is the rate constant at the higher temperature, minus the natural log of the rate constant at the colder temperature is equal to, and then the rest of the equation can remain as is. Remember that Tc and Th are temperature hot and temperature cold. What I'm trying to solve for is Kh. So let's plug in what we know. The natural log of Kh, and I'm going to go ahead and add the natural log of Kc to both sides of the equation. And so this is going to give me the activation energy, which right now is in 81.0 kilojoules. However, my R is in joules, so I'm going to go ahead and change my kilojoules to joules by multiplying it by 1,000. So EA is going to be 81,000 divided by R is 8.314 times 1 over the colder temperature, which is 300 Kelvin, minus 1 over the hotter temperature, which is 310, plus the natural log of the value of K at the colder temperature, which is 45.9. So let's plug this into our calculator. 81,000 divided by 8.314 times, open parenthesis, 1 divided by 300 minus 1 divided by 310, close parenthesis, plus the natural log of 45.9, close parenthesis. That's going to get us 4.874. However, that's the natural log of Kh is equal to 4.874. I still want to solve for just the Kh, so I'm going to take E to both sides of the equation. This is going to cancel out the natural log, and so E to the previous answer is going to give me my rate constant at the hotter temperature, which is 130.85 seconds to the negative 1, which is letter A. Number 2, consider a reaction that has a delta E of negative 20 kilojoules per mole. When this reaction is heated from 300 Kelvin to 312 Kelvin, the rate constant increases by a factor of 2.62. What is the activation energy for the back reaction? So first of all, let's kind of sketch out what our graph kind of looks like. And because it's a negative 20, that means it's exothermic. So that means that the reactants have a bit more energy than the products. These 2 points are separated by 20 kilojoules. And the question is, what is the activation energy of the back reaction? But first, what I need to know is, what is the activation energy of the forward reaction from this point to this point? So we need to find the activation energy. Given the information provided, we can use one of our equations that'll allow us to solve for activation energy given two different temperatures. And I'm going to use this equation because it's already set to solve for activation energy given the ratio here and the two different temperatures. So when we plug in what we know, the activation energy equals 8.314, remember this is joules per mole Kelvin, times the natural log of the ratio, which is 2.62, times 1 over the colder temperature, which is 300 Kelvin, minus 1 over the hotter temperature, which is 312 Kelvin. All this raised to the negative 1. So now let's type this into our calculator. first I'll work what's in the parentheses. I'll have open parenthesis 1 divided by 300 minus 1 divided by 312, close parenthesis, and all of that raised to the negative 1, which is going to give me 7,800. Then I'll multiply times the natural log of 2.62, make sure you close that parenthesis, times 8.314, and that's going to give me a value of 62,461. Remember, that's in joules. This tells me the activation energy of the forward reaction is 62.46 kilojoules. And so if I want to know what is the activation energy of the reverse reaction, that's going to be from this point to the top of the peak. And so it's a combination of the forward reaction's activation energy plus the delta E. And so that's going to equal 82.46 kilojoules, or 82,460 joules, which is the same as 8.246 times 10 to the 4 joules, which is letter A. Number 4, the rate of a reaction was found to triple when the temperature was increased from 28 degrees to 55 degrees. What is the energy of activation? So again, we have two different temperatures, and we're being asked what is the activation energy, and so I'll use this equation, number 4. So now let's plug in our values. The activation energy will equal, R is 8.314 joules per mole Kelvin, times the natural log of, and they tell us that the rate was tripled, and so we can say that it was raised by a factor of 3, and so this is going to be equal to 3 times 1 over the colder temperature is 28 degrees, and make sure we change it to Kelvin by adding 273.15, minus 1 over the hotter temperature, which is going to be 55, plus 273.15. And all of that is raised to the negative 1. And so let's type this in our calculator. I'll start with open parenthesis 1 divided by parentheses again 28 plus 273.15 close parenthesis minus 1 divided by open parenthesis 55 plus 273.15 close parenthesis, and all that to the negative 1 gives me 3,660. Now we'll multiply this times the natural log of 3, make sure you close the parenthesis, times 8.314 equals, and we get an activation energy equal to 33,430 joules, or 33.430 kilojoules, which is going to be letter B. Number 7. Consider a first-order reaction that has a half-life of 36.67 seconds at 35 degrees Celsius. The activation energy is 45.5 kilojoules per mole. What is the half-life at 155 degrees Celsius? So, since they use the terms half-life, we're going to want to look at our first-order equations, which are here, and here's the equation for half-life. So step 1 would be to use this half-life and determine what is the rate constant at this temperature. So basically the rate constant at the cold temperature. And so I will rearrange this equation and set it to solve for the rate constant. So I'm going to take the natural log of 2 and divide by the half-life, which is 36.67 seconds. And so I get a rate constant that is equal to 0.0189 seconds to the negative 1. Now, step 2, I'm going to use this Kc, and I'm going to use it with the equation that relates rate constant to activation energy. And so I'll go with the equation number 3, this one right here. I know the two temperatures, I know the activation energy, and now I know Kc, so I can solve it for the rate constant at the hotter temperature. I'm going to go ahead and separate this part right here, and I will get the natural log of Kh minus the natural log of Kc, which is 0.0189, is equal to my activation energy And it's in kilojoules, but I'm going to multiply that times 1,000 in order to turn it into joules. So 45,500 divided by 8.314 joules times 1 over the colder temperature, which is going to be 35 plus 273.15, minus 1 over the hotter temperature, 155 plus 273.15. I'm also going to go ahead and add the natural log of 0.0189 to both sides of the equation. And now let's go ahead and type this into our calculator. And once we do, we get the natural log of KH is equal to this value, and then we're going to raise both sides by E. That's going to cancel out the natural log, leaving me with just the constant KH, which is going to be 2.743. So now that we have the rate constant at the higher temperature, step 3 would be to use the half-life equation one more time, and now I can figure out what is the half-life at the higher temperature by taking the natural log of 2 and dividing by 2.743, which is going to give us 0.253 seconds, which is letter D.